In Chapter 9, it introduced the powerful tool of phase diagrams for describing equilibrium microstructural development during slow cooling from the melt. Throughout that chapter, however, we were cautioned that phase diagrams represent microstructure that should develop, assuming that temperature is changed slowly enough to maintain equilibrium at all times. But it does not provide information about the transformation of especially austenite to any structure other than equilibrium structures. And it doesn't provide any details about the influence of time or cooling rates on the formation of different structures. In other words, this iron carbon diagram we learned from chapter 9 does not explain the decomposition of austenite under non-equilibrium conditions or conditions involving faster rates of cooling than the equilibrium cooling. However, many structures, for example the martensite, which we will learn in this chapter, it doesn't appear on the equilibrium phase diagram, but it may be found in the microstructures in steel under non-equilibrium conditions, and those kind of microstructures are sometimes desired because they have some desired mechanical properties. In fact, in practice, materials processing, just like so much of daily life, is rushed, and time becomes an important factor. The practical aspect of this concept is heat treatment, the temperature versus time history necessary to generate a desired microstructure. So the fundamental basis for heat treatment is kinetics, which we shall define as the science of time-dependent phase transformation. Some information the equilibrium phase diagram cannot answer, including time. Transforming from one phase into another takes time. For the eutectoid reaction, we have FCC, austenite, and it will transform into two-phase microconstituents, which are includes the cementite and then ferrite, where your ferrite has a BCC structure. So this type of transformation definitely will take some time to finish, but your equilibrium phase diagram cannot show time, doesn't have any information regarding the time. So, and also, how does the rate of transformation depend on time and temperature? Like we cannot tell from the equilibrium phase diagram. Is it possible to speed up transformations so that we can have some non-equilibrium structures? But again, on the equilibrium phase diagram, only the equilibrium phases are shown. Some other questions, the mechanical properties of non-equilibrium structures, how can we figure out that? And are those more desirable than equilibrium ones? We cannot find answer from the equilibrium phase diagram. So as an analogy, think about you're gonna bake a cake, right? So the equilibrium phase diagram only tells you what the ingredients you need and at what temperature should you bake your cake. For example, you need cake flour and you need 2 eggs. You should bake it at 375 degree Fahrenheit, and that's it. It doesn't tell you how long should you keep your cake in the oven, right? And when do you need to reduce the temperature or not? It doesn't tell you this kind of information. And also, if you want to have a different textured cake, can we cook it faster with a higher temperature, or keep the cake for a longer time in the oven? Will that change the texture of the cake? Your equilibrium phase diagram cannot answer those questions or doesn't have those informations. To answer the aforesaid questions, we're going to introduce a new type of diagram, which is called a TTT diagram. But before we look at the TTT diagram, let's recall the equilibrium phase diagram first, because we're going to focus the eutectoid
steel or eutectoid alloy on the equilibrium phase diagram. So which is here, right from the austenite and transform into the pearlite under equilibrium conditions. Okay, that's the part we're going to compare with.
We just mentioned one limitation of phase diagrams or equilibrium phase diagrams is their inability to indicate the time period required for or required to maintain in equilibrium during the reaction. The rate of approach to equilibrium for solid state systems is so slow that true equilibrium structures are rarely achieved. So when phase transformations are induced by temperature changes, equilibrium conditions are maintained only if the heating or cooling is carried out at extremely slow and impractical rates. So in most of the cases, the transformation will be in or an equilibrium cooling. For an equilibrium cooling, the transformations are shifted to lower temperatures, which is termed undercooling. For example, for the iron carbon system, we know that the eutectoid temperature is 727 degrees Celsius. Again, this temperature is only for equilibrium phase transformation. In other words, if we keep the cooling rate very, very, very slow and to give it a long period of time for the transformation to finish or to complete to have equilibrium microstructure or microconstitute, then it may happen at this temperature. But again, in most of the cases, this slow cooling rate is impractical. So the transformation actually takes place at a temperature that is below 727 degrees Celsius. So in most of the cases, or typically, the temperature, the reaction is displaced 10 to 20 degrees Celsius below the equilibrium transformation temperature. So keep in mind, in the following discussions, when we talk about phase transformations, it happened at a undercooled or supercooled state, which means we cool quickly from the austenite phase, rapid cool it to below 727. So it will be an undercooled state for the unequilibrium phase transformation to happen.
What is a TTT diagram? It is the temperature transformation diagram. It describes the time required at any temperature for a phase transformation to begin and end. So here is the TTT diagram we're going to look at. So here we have the time scale and we have the temperature axis, and this line representing where the phase transformation starts, and the other line representing where the phase transformation ends. And the TTT diagram assumes the temperature is constant during the transformation. So constant temperature, right? Since your temperature is over here is the vertical axis, so constant temperature, we will have this isothermal line for a constant temperature. So now if we say the phase transformation will take place at 500 degrees Celsius, over here, the transformation will start at this point, and you can read the time from the timeline and will end at the other point, and you can also read the time from that line, and we can calculate how long the transformation will take. So it shows what structures can be expected after different rates of cooling, not only under equilibrium cooling. It graphically describes the cooling rate required for the transformation of austenite to pearlite, bainite, or martensite. So we're going to introduce those terms in the next slide. And this diagram also gives the temperature at which such transformations take place. So what is pearlite, bainite, and martensite? Actually, all of those are carbon and iron alloys with different shapes and arrangements. So first we have pearlite, which we already introduced from last class, right? When we look at the iron-carbon equilibrium phase diagram. So this is the two-phase lamellar microconstituent, which we have the alpha ferrite and we have the cementite, and that forms in steels cooled in a normal fashion or isothermally transformed at relatively high temperatures. And next we have the bainite. It is also a two-phase microconstituent. It also has the ferrite and cementite and forms in steel that are isothermally transformed at relatively low temperatures. And also it doesn't have that lamella microconstituent or lamina microstructure. The last one is martensite. It is the iron carbon with body-centered tetragonal structure, which we call it BCT structure. So it's a result of heat treat and quench. And the martensite is very hard form of steel structure. It's hard and brittle. Let's see how the TTT diagram is constructed. Well, we'll have this eutectoid alloy, and usually we have samples with eutectoid compositions, and the samples will be austenized, which means the temperature is above the eutectoid temperature, 727 degrees Celsius. So we only have austenite. So it's called the samples are austenized. And then we're going to cool it down quickly to a lower temperature. The temperature is below the austenite temperature. So in this example, we have the temperature 675 degrees Celsius. And then, very important, we're going to hold at this temperature. So the measurement is for a certain constant temperature. It's taken at this specific temperature. And again, in this example, we have 675 degrees Celsius temperature shown here. And on your TTT diagram, here is 675 degrees Celsius. So our goal is to measure the time at when the transformation starts and the time where we have 50% transformation finished and the time where the transformation is 100% completed. So the time, we're going to measure the time as well as the amount of transformation. After we're reading the time, right, 0% transformation is right before transformation starts. That's the time. We get the time, find that point with intersection with the temperature line. And the second point is when 50% transformation completes. That's the second time, is the middle point. And last point is 100% transformation finished. That's the other point. So now at this temperature, right, that's the line, and we have 3 points obtained from this experiment, the starting point, 50% point, and end point. And the same thing, we'll do the same experiment at a different temperature. For example, we'll hold the temperature, or we will cool the temperature quickly from austenite, from above the eutectic temperature to 600 degrees Celsius, and we measure the time. The transformation just starts. We measure the time, 50% finished. We measure the time, transformation is all completed. So we get another 3 points. And we'll do this over and over again. We will have a lot of sets of 3 points representing transformation starts, transformation halfway done, transformation completed. And then we're going to connect those points. So we'll see 0% of transformation, you see 50% and then 100% line. And now we have this TTT diagram finished. Clearly, a large number of experiments are required to build up a complete TTT diagram. So austenite to pearlite isothermal transformation, we have eutectoid composition where the C0 equal to 0.76% of carbon, and the transformation will begin at above 727 degrees Celsius, which means we are inside this austenite region, right? And we're going to rapidly cool to 625 degrees Celsius, then hold the temperature at constant value because we said based on the TTT diagram, or TTT diagram is an isothermal treatment. So here is what happens. Again, we'll start from austenite and quench it or cool it rapidly to 625 degrees Celsius. Then we hold the constant temperature at a constant value, 625 degrees Celsius. And here is what happens, right? At the green line, we'll have 0% of transformation, which means we only have this austenite at this time. And then at the middle line, at that time, we have 50% austenite transformed to pearlite. And finally, when we add the finish line, 100% transformation, all the austenite will transform to this lamellar microstructured pearlite. Austenite to bainite isothermal transformation. At lower temperature, austenite transforms to bainite. We said at higher temperature, we will have pearlite, but at lower temperature will be bainite. You don't have to remember or memorize everything because on this TTT diagram, this P means pearlite and B means bainite. So on the top portion means a higher temperature, you will have pearlite, but at a lower temperature, you will have bainite. So we said bainite is also a two-phase microconstituent, which will have the alpha ferrite and cementite. So it has elongated cementite particles in ferrite matrix, and it is diffusion controlled. So slightly different microstructure than the pearlite, but exactly the same microconstituent. This is the isothermal transformation diagram. Again, we're talking about the eutectoid composition, just the different cooling rate. So here the comparison. When we cool it down quickly to a higher temperature and hold it constantly at that temperature, if the temperature is above about 550 degrees Celsius, we will end up with 100% of pearlite. And usually we'll hold the temperature at 625, as we mentioned earlier. But below that temperature, below 550, we may have bainite. So here is one example. We're going to cool it a little bit quicker, all the way down to a temperature that is lower than 550. Looks like we are at about 475, and hold the temperature until the transformation finished. We will have the bainite.
So how do we tell from the TTT diagram that after phase transformation, do we have pearlite from austenite or do we have bainite from austenite? Well, if you take a look at this TTT diagram, it forms a C shape. So all three curves are C-shaped and have a nose at point N. Again, this point N is referred to as the nose of the TTT diagram. And at this point, or at the nose, the rate of transformation is a maximum. So the rate of transformation is the slope at any given point on the TTT diagram. So now you can see the rate of transformation at point N is a maximum. And now if we draw an isothermal line passed through point N, on top of it or above this point is P, refers to pearlite, and below this point we have B, which is bainite. So therefore, divided by this nose at about 450 degrees Celsius for carbon-iron phase diagram, pearlite forms above the nose and bainite forms below the nose. The temperature region for pearlite to form is between 727, which is the eutectoid temperature, and the temperature of the nose, which is 540. And for bainite is formed between 215 and 540. Again, that's the nose temperature. But note that the pearlitic and bainitic transformations are competitive with each other, which means once some portion of an alloy has transformed into either pearlite or bainite, transformation to the other microconstituent is not possible without reheating to form austenite. In other words, no matter for pearlite or bainite, it can only be formed directly from austenite. So austenite to pearlite or austenite to bainite. We cannot have bainite from pearlite or pearlite from bainite.
Martensite forms during quenching when the face-centered cubic lattice of austenite is distorted into the BCT structure, which is the distorted body-centered tetragonal structure, without the loss of its carbon atoms into cementite and ferrite. So there's no diffusion happens because it still has these original carbon atoms. And here is the isothermal transformation diagram for the martensite. So it requires a very rapid cooling. So you see this cooling curve in order to have martensite. So here are the martensite composition lines. We have 0% over here, and it's a horizontal line instead of those curves. And this is 50% and the 90%. And if we want to have martensite, we have to cool very quick to avoid the nose of this TTT diagram. So this is called the nose of the TTT diagram. So the cooling rate should be quick enough to avoid any transformation to pearlite or bainite. And the percentage of transformation depends only on the temperature to which rapidly cooled. So which means if we cool rapidly to about 180 degrees Celsius, then we will have a hold temperature, and then we will have 50% of martensite plus 50% of austenite. But if we cool it quick enough and all the way to below, for example, that's 100 degrees Celsius, right, to about 100 degrees Celsius, and then hold it, then we'll have about 90% of martensite plus 10% of austenite. So the percentage of transformation depends only on the temperature we rapid cooled to and hold at. Doesn't depend on the on the time really.
So from austenite, if we cool it slowly under equilibrium conditions, we will have two phases. One is the alpha phase BCC iron, one is cementite. And we have alternative layers of alpha and cementite. But if we quench from austenite fast or quick enough, we will have martensite. So martensite is just one single phase, and it has BCT crystal structure. It trapped all of the carbon inside this BCT structure. As a result, the martensite is very hard and brittle. However, we can do some heat treatment to restore the ductility of the martensite. So this heat treatment is called tempering. And tempering is carried out usually at 250 to 650 degrees Celsius, which is below the eutectoid temperature. So tempering is accomplished by heating a martensite or martensitic steel to a temperature below the eutectoid for a specific time of period. As a result, the BCT structure will turn back to, or one phase will become two phases again. One is the alpha pyrite and one is cementite. So this structure now from BCT for martensite to the two phases is called the tempered martensite. So the tempered martensite, again, from this equation or from this conversion, we can see it has stable pyrite, which is the alpha iron, and cementite phases, two phases instead of one phase. The microstructure is extremely small and uniformly dispersed cementite particles embedded within the pyrite matrix, and the resultant mechanical structure or mechanical property is the tempered martensite is as hard and strong as martensite, but with substantially enhanced ductility and toughness.
Here is the completed TTT diagram and how to use it as for the heat treatment of eutectoid alloys. P for porolite. The porolite is over here on the top portion at relatively higher temperature. Starting line, end line in the middle is the 50% finished line, and bainite, B is for bainite, is at relatively lower temperature. So bainite, this is the bainite start to transform line, bainite finished transform line, and all the heat treatment should start from above the eutectoid temperature, which means we should austenize the material, the alloy, before we heat treat it. So that's the A1, 727 degrees Celsius, the eutectoid temperature. And martensite is at the very bottom of this TTT diagram. Again, it has those horizontal lines, 0 martensite, and this is 50% martensite, and below it is about 90% of martensite. It doesn't depend on the time, only the temperature you bring it to. For example, if I quench it to about 220 degrees Celsius over here and then hold it at constant value, then I probably will just have austenite instead of martensite, because that's the 0% of transformation for austenite. And before those, or between the start and finish lines, you have that phase and the austenite, right? And that's the remaining austenite hasn't been transformed yet. And that's as well for martensite as well. This is M plus A, the martensite plus the austenite. Another very important information on this TTT diagram is on the right hand side, you have this HRC hardness values. So this is very important information for you to design your heat treatment process for the eutectoid alloy. For example, you want to have the alloy with a hardness number of HRC 42, right? It means we probably want to have bainite. Right? Bainite compared to porolite has a higher hardness or is more stronger. So here 42 is our goal. So that means to do the heat treatment, right? We want to start from the austenite above here, and we cool it quickly to a certain temperature. It's about 425 or 30 degrees Celsius. And then we're going to hold it, hold it, hold it. It's a little bit above 42, but you know the idea, right? It should be at 400 degrees Celsius, and then hold it, and until the transformation finished, and your final alloy will have a hardness of 42 HRC. Summary of possible transformations for austenite. If we cool it slowly, we'll have pearlite, which is a layered structure with ferrite and iron carbide, and also it can have a pro-eutectoid phase, which can be a ferrite or a iron carbide. And if we cool it moderately and to a relatively lower temperature, we may have bainite. And bainite is a mixture of alpha ferrite and elongated iron carbide particles dispersed into the alpha matrix. And if we quench it rapidly, we may have martensite, which has a BCT structure with iron and carbon, but carbon is not doesn't diffuse out from the originally FCC structure because the quench speed is too quick for it to diffuse, and the martensite is hard and brittle. If we reheat it, we'll have tempered martensite because these iron carbide particles will become finer, so it will be more ductile, lose some of these strengths, but will be more ductile. So as that being said, if we compare the properties, the martensite has the highest strength, and then will be the tempered martensite. Bainite, right? Bainite is has a higher hardness than pearlite, finer pearlite and coarse pearlite. Again, the finer the structure, the more stronger it will be. Think about grain size reduction, strengthening mechanism, and if the material is coarser, then it has higher ductility. Now let's compare phase diagram and TTT diagram one more time since we learned what is a TTT diagram in this class, right? So for phase diagram, it describes equilibrium microstructure development that is often at extremely slow cooling or heating conditions. It allows time to for its equilibrium state to reach, but it provides no information on time taken to form those phases. On the other hand, for the TTT diagram, for given alloy compositions, the percentage completion of a given phase transformation on temperature time axis is described. So it will give the time and temperature information as well as the amount of transformation. So usually we use both diagrams to help us design a certain material. Let's do one example on how to use the TTT diagram to do heat treatment. On the isothermal transformation diagram for a 0.45% carbon iron carbon alloy, sketch and label the time temperature path to produce the following microstructures. So remember now we have 0.45% of carbon is not the eutectoid composition we saw earlier. So the first question, we need to have 42% of pro-eutectoid ferrite, eutectoid ferrite, and 58% of coarse pearlite. I think it's worth to bring out the equilibrium phase diagram one more time to see where is the composition line and what is the pre-eutectoid ferrite and also the pearlite. Right? Okay, so here is the phase diagram. And we have the 0.48 composition line over here. So it's a pro-eutectoid alloy, right? It's to the left of the eutectoid composition. So that means first you have the pro-eutectoid alpha phase before the eutectoid reaction, right? And during the reaction, only the austenite will transform into the pearlite. So in other words, in your final microconstitute, you will still have this pro-eutectoid alpha, and then you have this austenite transformed, or the pearlite transformed from austenite. And then we're gonna do another pass to have 50% of pearlite with 50% of bainite, and then do another design to have 100% of martensite, and lastly do a design to do 50% martensite and 50% of austenite. And let's see how to do it. So first, we're going to figure out to design the path. The results will be 42% of proeutectoid ferrite and then 58% of course pearlite. At the beginning, we probably don't need to worry about the proeutectoid ferrite based on the TTT diagram, because the TTT diagram is always start from the austenite and then transform into either pearlite or martensite or bainite. So in other words, this proeutectoid ferrite will not participate in the transformation. So we'll just take a look at how to transform the remaining austenite to pearlite. Here is the design path. You start from, maybe I want to show that one more time. Cannot go. Okay, so it's from the austenite, right? And then we cool down to a certain temperature, about 680 degrees Celsius over here. And we hold it at constant and hold it until, well, we pass this finish line. So everything will be transformed to pearlite. But again, all the austenite is transformed to pearlite. The ferrite, proeutectoid ferrite, will not participate in the transformation. Okay, so now we can double check those values to see if we do have the required phase amounts or microconstituent amount. The problem asks for 42% and 58%, right? So since it's proeutectoid ferrite, we should draw a timeline between the just above the eutectoid temperature. So I suggest you bring out your iron carbon phase diagram to do this calculation one more time by yourself. The answer shows that if the original composition C0 is 0.45 or 0.45%, then your resultant proeutectoid ferrite will be point or 42%, and the pearlite will be 58% if the cooling is at equilibrium. Another hint is the weight percentage of pearlite actually is the weight percentage of austenite right before the eutectoid reaction. And this is the proeutectoid ferrite. Number B, 50% fine pearlite and 50% bainite. So we can design a two-stage heat treatment over here. Now, step 1, we're going to isothermally heat to about 590 degrees Celsius, this orange line, right over here, right above the boundary between the pearlite and the bainite. Here is the cooling line. And now we hold the temperature at 590 degree all the way to the 50% line, because we want to have 50% of fine pearlite only. So we stop here. The next step will be isothermally treat at 470 degrees Celsius. So at a lower temperature within the bainite region. So that means we quench it or we cool it rapidly again to a lower temperature. This temperature we choose 470 degree over here, and the remaining austenite we hold the temperature again, right? The remaining austenite will start to transform all the way to bainite. So why this line kind of reversed in time? Actually, it's not reversed in time from this point to the other point. It just means the transformation is from the austenite phase. This region you have austenite A, right? Austenite phase, and transform to the bainite region. So the remaining 50% of the austenite will become bainite. So as a result, you will have 50% of pearlite and 50% of bainite. So another side note is fine pearlite. In the earlier number A, you have a coarse pearlite, right? So actually, within the pearlite region, we have two types. On the top portion, you have the coarse pearlite, and on the bottom portion, you will have the finer pearlite. So this TTT diagram doesn't have those details, but some other TTT diagrams will have the details given. Again, on top, if you cool it quicker or to a higher temperature, you will have a coarser microstructure or coarser grain. If we cool it to a relatively lower temperature, but still within the pearlite region, the grain size will be smaller, which will be finer grains. Number C, we want to have 100% of martensite. So this one is kind of easy. We just need to rapidly quench to room temperature because based on the TTT diagram, martensite start to form 50% and 90%. We want to quench it to a temperature that is below far below this 90%, for example. I think here, right, you will already have 100% of martensite. So that's the quenching line. Quench it right all the way to a very low temperature, then you will have 100% of martensite. The last one is 50% of martensite, 50% of austenite. So just quench it along that blue line. We're gonna quench it all the way to this 50% line and hold it. Then you will have 50% transformed to martensite. The other 50% will still be the austenite.